we're trying to talk her into moving, or not her, more or less her husband, because he wants to stay. He loves that stupid house. It's awful. It's the grossest house I've ever been in. And then their well, they used to put a bunch of detergent from leftover wash, like in their washing machine, and they made the whole well sour. And he still wants to stay there. It's like not even half an acre.
Interesting.
Oh my gosh.
Did he grow up in that house?
No, he didn't.
Okay, we should get started here. All right, so here's the deal. Hey, how did the assignment go with the trig rules, with the trig differentiation stuff?
I finished it, I just don't remember doing it.
Yeah, that's just it. Okay, so the trig stuff is not really all that awful with the differentiation. I mean, once you know the basic pattern, derivative sign is cosine, derivative cosine is negative sign, you can apply that to get the ones for the quotient, use the quotient rule to get the cosines and the tangents and the cotangents and so on. So, you know, those ones are not really so bad. And I hope you're starting to feel like you got this giant brain going, because this is getting to be some pretty fancy stuff that you're going to be able to use to solve all kinds of impressive problems. We need another tool, though. An important tool called the chain rule. Now, here's the deal. I used to teach, back when there was an atmospheric science program at Creighton, one of the classes we taught was sort of the refresher of math before they took the more math-oriented classes. And one of the things they had already taken was Calc 1. And a lot of stuff that we do in atmospheric science, you need to use the chain rule to compute the derivatives, and they always had forgotten that. And it is my experience that the reason why is because they never really learned it right in the first place. And a big part of the reason why is because the way textbooks explain it, they make such a mess of the notation of how they're writing this, that it just becomes a big tangled mess. So what we're going to do here is I'm going to show you how to solve problems using the chain rule before we take on the mess that is in your book of how all these different, how we're going to write this down. Let me give you an example of the kind of problem we solve using the chain rule. If you have some kind of function, f of x, that looks like this. How about 3x squared plus 1, the whole thing to the 6th power? The truth of the matter is this could be solved already using stuff you know how to do. It would just be horrible. So I want you to find the derivative. Find the derivative with respect to x of f of x. That's the same thing as saying f prime of x here. All right, this is a solvable thing without the chain rule. Not all of them can be done without chain rule. But what could we do with this? We could sit here and expand all this out. We could have written down 3x squared plus 1, the quantity, times 3x plus 1, write it out 6 times and start foiling. Foil, 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 foil. You'll get this giant polynomial. Well, the derivative of a polynomial is not so hard. We have those power rules for that kind of thing, right? Turns out this is not such a bad thing, though, if we can use the chain rule. Now, what are we going to do with the chain rule? When we are using the chain rule, I'm going to get another color here. The markers that they left us in here, they left the caps off on, so I have to start repackaging. They're all dried out. All right. What we do when we use the chain rule is we see if there's a function inside of a function. Like, for example, in this case, this thing right here is it's evil enough for its own day. Right? Let's just treat that like something. I always think a. Well, whatever. Then this would just be a to the 6th power. We can just treat this like take the derivative of that a. Well, that would just be 6a to the 5th power. But I'm going to put some dot, dot, dot. We're not done here yet. That part doesn't look so bad. Then I could just put that, it's going to really be 6 times the quantity. We've got to put that, what's back in there for that a, 3x squared plus 1, that whole thing to the 5th power. But I'm going to put dot, dot, dot here because we're not done yet. Then we take the derivative of the a part. So what is the derivative of this thing? If we had a prime, what is this?
6x.
6x. So then we just multiply this then by that a prime. which in this case would be 6x. Now we got a little bit of algebra to do here. We would pull that 6 over here and make that 36x times the quantity 3x squared plus 1 to the 5th power. See what we did here? We treated the function inside like its own little beast. And just did the derivative, just carrying that little a around or whatever. And then we multiplied that by the derivative of that a. And that's the chain rule. And let's just do a couple more examples before we try to come up with some way to denote this. Let's do another one. How about, if this was f of x was equal to the sine of 3x squared? Find the derivative of that with respect to x. Again, there's sort of a little function in here, and then we take the function of that, f of this thing. And again, I always think of it as a, but I think that's just the way Father Ports taught me that when I took Calc 1 at Creighton 30 years ago, or 25 years ago, whatever it was. And so I just think of that as like a little a. Well, the derivative of a, the derivative of sine of a, this becomes just like sine of a, is no big deal. That's just derivative of that is cosine of a, dot, 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 dot. We're not done yet. And that cosine, okay, cosine, let's put that back in there, that a is 3x squared. But then we're going to multiply that by the derivative of the a. Where a is equal to 3x squared, so the derivative of a is 6x. So yeah, we usually rearrange this a little bit to make it look a little better. But 6x times the quantity, 6x times cosine of 3x squared. It's the derivative treating the inside part like a chunk that we can just sort of replace with like a letter or something, times the derivative of that inside chunk. We just said, let's leave this, let's forget about this part for a while and just treat this like sine of a. Well, derivative of sine is just cosine of a. But because of the chain rule, then we got to take the derivative times the derivative of the a itself. Okay, so cosine of 3x squared times the derivative of a, which is 6x, and then we just sort of rearrange it to make it nicer, which you don't have to do. There are rules about how to rearrange that to make it look nicer, but they're just sort of, it's fine. Let's do one more before we try to come up with some notation here. How about f of x is equal to sine x plus cosine x let's just keep this pretty straightforward. 4 to the cube, 4th power. So the derivative of this, I'll just write it as f prime of x. Again, we have this outer function, we have something that we're cubing, taking to the 4th power, and we have this inner part. And let's just treat that inner part like a chunk for right now. This thing right here, it's just a thing. I'll say a. Then, okay, this is just the derivative of a to the 4th power, that is 4a cubed. And now we know apparently from our chain rule that we're going to be multiplying that by a prime. So then this will be 4 times that a times the derivative of this. What's the derivative of sine?
Is it cos minus sine?
That's right, it's cos minus sine. And that would be fine. You don't need to multiply all that out or anything like that. Your book makes a mess of this. Every calculus book makes a mess of this. They try to talk about this as the derivative with respect to x of some f of g of x is equal to the derivative of f of g of x times the derivative of g of x. Which is factually correct. But I don't think that's very helpful to see it written that way. Or sometimes they'll use it during these d's, where like the derivative with respect to x of f of g of x is written as the derivative of f with respect to g times the derivative of with respect to x. I don't know that that's all that helpful. Well, I mean, I get it in like a 500 level math class why that becomes more important, but for right now, I don't see how. The chain rule is better learned how to use it than how to write the rule itself. Okay? That doesn't strike me as the important thing. The fun, such as the fun, begins when we start combining the chain rule with other rules. Then it starts becoming trickier to start to figure out what's the inner and what's the outer part of the function. For example, what if we had a function that was sine of x, I'll just put parentheses here to help, times cosine to the 4th power of x. We clearly have a product here. We are clearly multiplying two things, sine of x and cosine to the 4th power of x. That is a product rule thing. Let's see what we can do with that. So our derivative of this, f prime of x, or the same thing we could write as derivative with respect to x of f of x, is equal to, well, we got to use our product rule. First, I'm going to write it out using the tick marks. Remember, it's the derivative of the first term, I'll just write with the little prime right there, times the second term, plus the first term, times the derivative of the second term. I'm just putting it there with those tick marks. Okay. Derivative of sine, we learned last time. Derivative of sine is cosine times the second term, plus the first term, times, oh, wait a minute, derivative of cosine to the 4th power. Now we have a chain rule. Let's go bust that off into a different place in a different color. The derivative with respect to x of cosine to the 4th power of x. Okay. In case you're not clear about that, that's the derivative with respect to x of the cosine of x all to the 4th power. That's a chain rule problem. Where like our a is this thing on the inside. So this is going to be 4a cubed a prime. Where 4 cosine cubed x times the derivative of cosine, which is negative the sine. Plug this bad boy back in. Negative 4 cosine cubed x sine x. Then you had to have to do some simplifying or factoring or something like that, and I don't care that much. It is a common problem on these, because these chain rule things tend to produce answers that have lots of terms that are similar. I mean, what do we do with this? Like, do I want to combine these things together and make it cosine to the 5th power minus 4 cosine to the 3rd power x sine squared x? Okay, I don't care. That seems fine. I don't care. Do we want to then maybe factor out a cosine cubed? Maybe. Cosine squared x minus 4 sine squared x? Maybe. I don't know. I made this problem up. I don't know where we're going to stop. You're not going to lose points that you didn't like do enough algebra and rearranging. Okay? That's not the point. The point is the correct application of the chain rule. Okay, so that was a product rule with a chain rule inside of it. First we had to expand the product rule, derivative of the first times the second, plus the first times the derivative of the second, but this bad boy was a chain rule. That derivative of that term, we had to use a chain rule on. All of our rules we could have related the chain rule. Let's try another one. How about f of x equals, how about a chain rule of a quotient rule? How about sine of x squared over sine x? Oh my. First off, why would you ever need such a damn stupid equation? No, I'm just making them up. But physics and engineering and business are full of weird equations. Alright, so here's your weird equation. Clearly, it is a chain rule. We have this weird thing on the inside that then we take a function of. We could say this thing right here, we're going to call that a. Where then the derivative with respect to x of f of x is equal to the sine of a. Well, it's the derivative of the sine of a. It'll be the cosine of a, and then we know it's going to be times the derivative of a. So we already got the outer part here. Cosine of x squared over sine x. Well, we got to figure out this derivative of that a. Well, that's clearly a quotient rule, which prior to about a week and a half ago, I could have recited off the top of my head, but now Matt has got me confused with the low, d high, d low, or whatever. It's
Low d high.
Low d high, okay. Alright, so what is this? A prime, the derivative here. So it is low times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Alright?
Yep.
Alright. So, it is the cosine of, I know I'm going fast, hold on, times, oh boy, sine of x times 2x minus x squared cosine x sine squared x. So if this equation here, this weird stupid thing, describes, I don't know, the position of a ball, or a rocket or something like that, like how high above the ground it is, the derivative of that is describing the speed at which it's going. Or we could even take the second derivative. That would be a horrible beast. What if we wanted to do that now? Oh, the horrible textbook says, now take the second derivative with respect to x of the same thing. So you're going to take the derivative of this thing. Oh my god, it would be a nightmare. But it could be done, right? We would have to break this thing up into, it's clearly a product. So we would take the derivative of the first, it sounds like a beast already, times the second, plus the first times the derivative of the second. The derivative of this thing would be a quotient rule. Oh my god, it has this thing in it, which is another chain rule. But it could be done. It just would be no fun at all. So it's very, very possible, and that's the kind of thing that happens in homework sets, to have some problems that are just chain rules, like what we did at the beginning. But really what tends to happen is they tend to start tying it together to other ideas. A chain rule of a product rule, or a chain rule of a quotient rule. Hey, what about a chain rule of a chain rule? Sure can do that. Let's see if I can figure that out. A good example. F of x is equal to the cosine of the sine squared x. What an ugly problem. So we have some equation, I don't know, this describes some complicated motion of something. We want to know its derivative so we know its velocity at any given time. Or this is the rate of growth of something. I'm sorry, this is how much the population of some bacteria is or something, and now we want to know the rate of growth by taking its derivative or whatever. Well, this is clearly a chain rule. We have a cosine of something horrid. Let's take that something horrible on the inside and say, it's evil. That's from the Bible. It's evil enough for one day. Right? Let's just leave it, let it be its own evil for a different day. So we're going to put this on right here. Cosine of A. So the derivative with respect to x of this thing, or f prime of this thing, to use that notation, will just be derivative cosine. That's negative the sine of A But then we're going to have to multiply that by the derivative of a. Okay, let's figure that out. The derivative of a is going to be the derivative of sine squared of x. That's the derivative with respect to x of sine squared of x. Well, that's actually another chain rule. I mean, that's saying, let's write it this way. Sine squared of x, like that. Well, let's call this thing on the inside, I don't know, for lack of a better word, how about we call that b? So this is the derivative of b squared. Well, that'll be 2b times the derivative of the b. It's a chain rule inside of a chain rule. So we've got 2, well, that b is sine of x, and b prime, the derivative of sine of x, is cosine of x. Equals 2 sine x cosine x. So this thing, which was a prime, goes back over here. Negative the sine of a, oh, let's replace that a with sine of sine squared x, and then that a prime, 2 sine x cosine x. Oh my god, what a mess. I just made that problem up. I mean, there would be necessarily better examples and so on. Again, it freaks me out every time I talk quantitative methods in the atmospheric sciences, how bad different calc textbooks do at just writing the chain rule out. It's so much easier to just do it a bunch of times and recognize the pattern. When you've got some kind of function and inside it there's another function, that's a chain rule problem. Taking the derivative of that whole thing then means derivative of the outside times the derivative of the inside. It just takes some practice. I want to do one more for sure. Alright, how about this? How about f of x is equal to, let's just stick with a cosine of a product. How about 5x squared sine x? We've got a function, cosine, of something inside of it, that itself is a function, 5x squared sine x. The derivative of this beastie, well, let's just get rid of this thing. Let's call this thing a. Cosine of a, its derivative is no big deal. Derivative of cosine is negative the sine. Negative the sine of that thing, and then what the chain rule tells us is times the derivative of that thing itself. Cosine, in this case, then it's negative sine a times, if a set of parentheses here will help you, times the derivative of a. But derivative of a itself, in this case, what rule is that? 5x squared times sine x. That's a product rule. We got something times something. So that derivative of a itself is a product rule. We're going to need derivative of this term times this term. Let's see. 10x times sine x plus the first term times the derivative of the second term. Derivative of sine is x is cosine of x. So this beastie, which is x prime, will go into here. And you get negative the sine of a, but a is 5x squared sine x times that whole thing, 10x sine x plus 5x squared cosine x. Oh my god! These things can get very messy. Yep. And they're all over the place in physics and chemistry and business and engineering, because lots of things you need to know the derivative of are themselves dependent on other stuff, right? The rate of change of temperature, that is the heating rate, itself might depend on, it's a function of other stuff, like I don't know how the thing thickness of the material is changing or something like that, right? There is a function of a function. Happens more often than not in the natural world and physics and engineering and business and so on. All right. So we gotta do some problems about this bad boys. Where are we at here? Here's this. That is done. All right, where did that list of problems go? There it is. So, our problems for today are on page 297. Man, we are really flying through this book. 297. They are problems 221 through 237 odd, and also number 241 and number 253. All right. Take on those problems, and I will be glad to entertain any questions. So I'm going to get this started uploading, though, to YouTube.